let's look at a few chromatography examples. And I'm gonna focus on actually paper chromatography or thin layer chromatography, just because this is what we'll be doing in lab as well. But the same principle applies to liquid chromatography, HPLC, or gas chromatography. And it's just like, which of the two things in our mixture are going to get to the finish line, I guess, first. And that's just the end of the column or the end of the paper. So let's look at an example where we have a polar stationary phase. So maybe we have something like our stationary phase is going to be the paper. And so cellulose is going to be polar. And so we can use that. And then we'll have a non-polar mobile phase. So let's say we had a mobile phase that was something non-polar. Let's call it something that's just carbon and hydrogen. Maybe it's like hexanes, or benzene. So benzene is a 6-membered carbon ring with hydrogen bonds. It's very non-polar. Okay. So if we set up this system, and we would start with our sample right here on this X, and then we would place it into our benzene, and that benzene would travel up the paper till it got towards the top, and then we would pull it out so that way the separation stopped. And let's say when we do that, we see 2 spots that have moved. So our sample had been spotted right here, and now we see 2. We see an orange one and a green one. And one of them has moved further up the paper, and one has moved less up the paper. So let's figure out which one of these 2 possible compounds would be green, the green dot, and which one would be the orange dot. So I have 2 compounds that we'll pretend we're in a mixture together. Pinene, which is a terpene, and it's all carbon and carbon bonds and carbon hydrogen bonds. So it is, we would expect to be a non-polar compound. And I have another example here where this is a benzene ring with 3 alcohol groups, oxygens bonded to hydrogens. And so this will actually make a polar compound. So these 2 compounds that have gone through this phase. So in this case, my stationary phase is polar. And so the benzene ring with the 3 OH groups is going to be most likely to form strong intermolecular forces with something else that is polar, like our stationary phase. So this is similar IMFs to our stationary phase. And our pinene is nonpolar, and so it's actually going to be really similar to the benzene. It's going to have similar intermolecular forces with our benzene. Remember, like dissolves like. So really, of these 2 compounds in our mixture, the pinene is most likely to dissolve in our mobile phase that's moving up the paper. So we expect our nonpolar pinene to travel best with interact best with the mobile phase and travel up the paper faster. While our benzene ring with the alcohol groups is polar, it's going to be attracted to and interact with the stationary phase of the paper. And so it's going to move less slowly because it's going to have to break those interactions with the paper to move up the paper. And so we're going to see our polar compound is going to be lower on our paper, or separate out second, and our non-polar compound, the pinene, will be the green dot that's further up the paper. Now, if this was liquid chromatography or HPLC, it means that our pinene would come out of the column first. Same with gas chromatography. The vapor of the pinene would come through the column and exit it before the other compound with the alcohol group stud. All right, let's look at these same compounds, but now let's imagine that we have a nonpolar stationary phase. And so now we can imagine this thin layer or paper is nonpolar. And we're going to have a polar mobile phase. Let's assume it's dichloromethane. So this is polar. All right, so that's going to be, so this time we're going to have a polar mobile phase and a non-polar stationary phase of the paper. So let's keep our color coding the same so that way it doesn't break our brains too much. Our pinene will be the green dot and our benzene ring with alcohol groups will be our orange dot. So now the question becomes, is the orange dot going to be higher up, or is the green dot going to be higher up? So as our solvent comes up, we'll stop it here at the top. What we're going to want to ask ourselves to figure out which one goes the closest to the top or comes out of the column first for liquid chromatography or gas chromatography is which one will interact the most or have the most similar intermolecular forces as our solvent. Well, our solvent is polar, and we've already identified our benzene ring with the alcohol groups as polar. And so this is going to interact with, or it's going to have similar IMFs to our mobile phase. And our nonpolar pinene is going to be very similar to our stationary phase. So that means that orange dot is going to travel faster with that mobile phase, and we're going to have the orange dot towards the top this time and the green dot towards the bottom.